Welcome. Hey, everybody. It is I, Marc Dantonio. Welcome to SkyTour LiveStream. This was sort of a last minute, but it's a stream we're putting on for all of you and our friends out at the Phoenix MUFON out in Phoenix. Hello to Stacy. Hello to Marianne. Hello to James and the other people that are out there watching. It's nice to see you. Thank you for coming out and checking us out. And also, of course, we have Daryl Mason with us. Hello, Daryl. How's it going?
Hello, Mark. I'm good. You? Hello, everybody.
I'm doing fine, thank you. Everything is good. I figured we'll stream here before the Super Bowl and all that. Hey, Sean Farva. Sean, that's Sean out there. He's giving us, that's Farva. Thank you, Sean. That's very kind.
Thank you, Sean.
This is the Comet. This is the wonderful Comet that we're so used to seeing. This is the Comet. I'll put that out there for you. It's Comet C2022 E3 ZTF. ZTF stands for Zwicky Transient Facility. If you've been with us over the last few days, you notice also that there was a Barbarina Zwicky in the chat. That is the daughter of Fritz Zwicky, who is the man who pioneered such things as dark matter and other amazing astrophysical concepts. He was a hero of mine in many ways. We talked about him many times when I was getting my astronomy degree.
Did you know Fritz Zwicky is the guy who coined the term supernova?
Yes. That's right. It was not just him. There was one other guy that did that with him. But Fritz Zwicky... Huh?
Bada, I think was his name. B-A-A-D-E.
Yeah. And so... Fritz Zwicky was a pioneer in astronomy, and he was a Swiss astronomer, born in Bulgaria. And the ZTF on the end of this name here, as I said, stands for Zwicky Transient Facility. What's that? It is a automated telescope on Mount Palomar on the Oschin, O-S-C-H-I-N telescope. And it is used to robotically search for transient objects, which are comets. They're here and then they're not, right? Because they take time to come and go. And the ZTF facility has found a number of objects. In fact, it was a few days ago on the 6th of February when in the same field as this comet, we had another comet right there in the same field with it, right? Yep. So the Zwicky Transient Facility has found a lot of them. And it also looks for other things as well. Very successful robotic automated system. In any case, I just wanted to let you guys know that because it's kind of cool. This is the Comet as of now, and this is a live view, by the way. This is live. But what we'll do, just because, we're going to take a exposure and just, again, to point out to you, what we do here and how it works. All right, this is kind of important. We only pay attention to like this line right here. This is the exposure, all right, and you only need to pay attention to it. I pay attention to everything. And then this is the gain. This is the sensitivity of the sensor, and this is the exposure the length of time we're capturing light on the sensor. All right. So that's the important thing. So this area here, this is the camera setup and so forth. This down here, which will light up in just a second. This here is the focusing section down here. This is how we actually tell the telescope to focus itself. All right. And then over here, this is the telescope control section. All right. This is the telescope computer with its guiding. This is the telescope in the building. This is me. Hello. And then this is the main view, which is always a great deal of fun. So that said, we'll just let me just connect up our systems here. I'm still in the setup process. I haven't finished doing the full setup yet. Oh, there we go. All right, so let's connect. There we go, all lit up. And now what I'll do is I'll do a critical focus. So what we do is we move the telescope back out of focus a little bit. And you'll notice that the stars are going to get kind of fuzzy and look like little tiny donuts. All right. And there we are. So you see our little tiny donuts. And then we're going to go in and start the focus process. So we're going to now tell the focuser to go through a series of steps. And some of those steps will be in perfect focus and some will not. And so it's going to make a curve, a little, bell-shaped curve upside down. And like it's a parabola, and it's going to go like this on here. And that will bring us to our perfect focus. Then we'll take some exposures and see how it looks. We've captured this comet when it was much closer to us, and now we're capturing it as it's moving away from us. Again, a transient object. But I want to say hello to everybody that's watching. First of all, let's say hi to the person who made it here first, and that was Fantasy. Hello, Fantasy. C&D Boy in Canada has made it here now and to see us, and that's great to see you as well. Farva's with us. How you doing, Sean? Renee Cruz. Hi, Renee. How are you? Nice to see you. PG, that's Petita in Pennsylvania. The Pennsylvania Petita. And we know her very well. She's very sweet and a good person. Sam Mess is here with us tonight. Nice to see you, Sam. And we have a few more that are coming in. Robin Curtis has joined us tonight. Drop a Deuce is with us. Hey, drop number 2. Nice to see you. Thank you for coming by. Cindy Murphy's with us as well. And Mark Nelson's with us. Hey there, Mark. Mark Nelson is also a client of ours as well. So it's nice to see you, Mark. Well, you won't be able to see. Mark says, I still haven't seen it live. Well, it's harder now because it's fainter. So you're going to have to use a pair of binoculars and a dark sky to see it now. That's for sure. Okay. And we have Tricia Ferreira. How are you, Tricia? Nice to see you. And we have, let's see, I saw somebody else here that I haven't seen before. And I'll find her again. Izabela's here. Hi there, Izabela.
Izabella's here. Hi, Izabela.
Yeah. Yeah, and M. Turner. There we go. How you doing, M. Turner? Good to see you. Yeah, so it's good to see you. All right, so we are here, and we have our best focus position. So I'm going to there it is right there. Tell the telescope to go all the way out and all the way back into focus and bring us into really sharp focus. And now we're going to have a stunning, sharply focused system. Look at how pinpointy those stars are. Isn't that beautiful? So now what we'll do is we'll just take a 15-second exposure of the comet just to get a baseline. I haven't done it yet tonight. So this is the first photo we've taken of the comet today. So that'd be kind of cool. Let's zoom in a little bit and move it up a little bit. Okay. All right, here it comes. All right, that's gonna work. Okay, so we'll live stack this and we'll clear this stack. The moon is not up right now. The moon will be up later, but somewhat later. We got time. Hello, Flames. Flames of War is here. And is that Northeastern Pennsylvania History and Archaeology? Hello there. How are you? Nice to see you. Make sure you subscribe. Hang out with us. It's just going to be beautiful here. Let's color correct so we don't have that. And now let's do this. Oh, I've got this on. Sorry. Let me knock off this histogram. It'll be looking beautiful. All right, here we go. There we go. Yeah, there's our beautiful comet. Let me take the name away for a minute because we don't need that right here. So you come over here. All right.
There's a big red fringe on the left side.
Thank you, Mr. Red Fringe. It's that's actually from the flat frame. I will get rid of it.
See a little bit at the top right too.
As I said.
Yeah, I know.
Let me do this. Okay, we'll try that one. And I saw that earlier and I was like, well, we'll clear it. And this next one should be a little different. All right. See, the flat frame corrected it. There we go. Look at that. That's a pretty comet. Now, it has a blue plasma tail that's here, but as it moves further from the sun, that plasma tail is going to get fainter and fainter and fainter. And some nights it's very obvious to us, and some nights it's not. But we'll see.
Yeah.
Flames of War says, can't wait to see this beautiful thing that's about to pass. This actually already has passed us. It was closest to us, was that the 12th? No, not 12th. What am I saying? 12th. 10th. No, that was when it was at Mars. What was
closest to Earth?
Yeah, that was the 3rd or something.
February 1st.
Was that the 1st? Okay, I can remember.
It was at perihelion, closest to the sun on January the 12th. Closest to Earth on February 1st, and it's been in the neighborhood of Mars here the last couple of nights.
Yeah, Mars is actually just well, I'll show you where Mars is. Let me bring up our planetarium that's connected to our telescope. There's Mars. So if we zoom out here, you'll see that it's just south of Mars right now. So now in our telescope, you need to understand that Mars doesn't look that good because this is a wide field telescope. Our view that we're looking at right here, let me just set this to the automatic sizing so it fills the screen. This is 4 full moons across and 3 full moons tall. The moon's half a degree, so it's 4 across, so it's 2 degrees, and 3 tall, so 1.5. Okay, so that makes this field really large. So Mars would be kind of small. The planets are kind of small. Our next telescope, though, that we're adding to our SkyTour LiveStream suite of telescopes is going to be a higher focal length instrument, which means it's going to be more magnification, and we're going to be able to look up close at things like the planets and do crater dives on the moon and stuff like that. So that's where we're heading. So we'll have that. Marianne Robb is here. Hey, Marianne. Genghis is here. Good to see you.
Hi, Marianne.
Robert Waters is here. Oh, Robert says, to live under dark skies again. I know. Tell me about it. Tell me about it. And is Maya Leone here with us tonight? Someone said hi to Maya, so she must be
I see that. I don't see Maya yet.
She must be... Oh, there she is. She's up there. She says, hello, fellow Skywatchers. Well, hello, Maya. I'm so good. So glad to see you again. All right, so this... Now, what I'm going to do...
Oh, there she is.
Yeah, she's up there.
Maya, I have to say, you really spun our propellers here the other night when you asked for the Medusa
She did.
cluster, and we found the Medusa Nebula.
Yeah.
We've been going back to that. It's really beautiful.
Yeah, it really is. Thank you, Maya. That was a beautiful accidental stumble onto something gorgeous. And we'll be looking at... We could probably look at it again tonight, too. Hello, Lysiana. How are you? Hello, Tim F.
Barbarina's Rookies here.
Barbarina, hello. Good to see you. Yeah, Barbarina says, good evening. It was in May of 1934, Zwicky published the co-authored paper that made him famous, and that brought supernova into popular language. Nova. Yeah, we actually mentioned that earlier, Barbarina. In fact, that he coined the term supernova. Thank you so much. So there is our excellent and beautiful comet. Okay. Now, you'll notice when you look at the comet, you'll see that it has this section right here. This is the dust tail of the comet. This is this part here is known as the coma of the comet. That's sort of like the head of the comet. But then, very faintly, and it is very faint, along a line that's right about here, okay, is the blue plasma tail of the comet. And when we actually take some deeper photographs of it, we might be able to see it, but as it gets further from the sun, it's going to get fainter. Okay, but so we'll look for that later. I see it right here. It's very faint. But there are nights when it looks gorgeous. There's nights when it's kind of faint. All right, so let's color correct it. Maybe that'll help us. Didn't seem to do it. Didn't seem to make a difference. Because we're actually pretty well color corrected. I could try something else. No. Let me try that again. Yeah, you can see the tail just a little bit there. So if we actually bring this in and really, really blow it out, you can see
I see it faintly, yeah.
Right there, very faint. But that's what happens, and eventually the coma will be very, very faint. The dust tail will be almost non-existent because there will no longer be outgassing and pushing particles off the surface of the comet to fall behind the orbit of the comet and make the dust tail. And then once it gets into the outer solar system, it'll once again fall into an inert state where it will no longer be propelling material off its surface, will no longer be shooting a plasma ion tail back from interactions from the sun on the surface because it'll be too far away. So this is why these are wonderful transient objects to check out. Again, this is, bam, our favorite Comet C2022 E3 ZTF Zwicky Transient Facility Discovery. Very nice.
Mark Nelson, yeah, Halley's Comet came through in 1910, and there was a lot of talk about Earth passing through its tail. I don't know so much about, they said it lit up the sky, but it was a close pass, and Earth supposedly passed through the tail. And we've talked before how a science popularizer at the time,
Camille Flammarion,
named Camille Flammarion, said to the public that when the Earth flew through the comet's tail, that everybody might get poisoned by the cyanide gas. And that upset a lot of people, and people looking to make a buck jumped on it instantly and started peddling comet pills and patent medicines and you name it. And well, we're all still shaken, so you know, it didn't come to pass.
Yeah. And that reason was the reason that happened at all, and the reason he said that at all was because of the fact that when we look at the comet, you can't help but see this green glow. Well, that green glow is in large part due to carbon molecules, all right, that are being ionized, and when they are ionized, they will effectively give off a green glow. But there's another compound that's causing some of the green glow as well, and that is cyanogen, which is a carbon atom and a nitrogen atom. Okay, so a cyanogen will glow green as well when that molecule is ionized. And so it was the finding of cyanogen in the coma of comets in general that prompted Camille Flammarion to say that. Now, I don't think, and Daryl wasn't implying that he was trying to frighten the population. He wasn't. He was just stating the obvious. Comets have cyanogen, and it's possible that if we, and he was just being a scientist, a science guy. If we flew through the tail, then he didn't know it wasn't very dense. He thought it was dense. He said we could be in trouble if we flew through the tail. But he wasn't trying to scare anybody. He was just speaking science-y. And of course, it came back to haunt him. And it turned out not to be true. Of course.
Flammarion was like the Carl Sagan of the day back then.
Yeah, he was well respected, but he had his detractors.
Yeah. Well, the comet still looks nice.
It does. I
think we kind of get the feeling it is moving away from us, so it's getting smaller and smaller.
Yeah, I see. I'm going to clear it now and wait for this next quick shot to come in. Again, we are at 15 seconds of time. We'll go to a 25-second shot here in a minute. Okay. You'll notice it's sort of noisy, but you can see the size of the coma. I want to reduce that in size so you can kind of see it. So you see those two stars kind of looking like in a direct line. We'll check on those two stars in a little while, and you'll see that they're no longer in a direct line with the center of the comet. And when I say a direct line, I'm talking about these two stars right here, right? So if we were to draw a line right here and draw right through, it's just at the top of the comet's central nucleus, right? So that's the idea. We're going to see where that is in just a little while. And I promise you it won't be there. Right? So, in fact, if the comet was moving somewhat rapidly, I just erased it to start again, you'd notice a change very quickly within just a few minutes. Okay? Now, I just did this again. And now look. It's already different. You see that? Line through this now will no longer hit the top of the comet. The central nucleus of this comet is now below it, which is kind of weird. Let me that could be an artifact of my system, but I'm going to make sure. No.
There in Stellarium, cosmic ray had asked if that's T Tauri to the right of the comet. Yes, it is.
That's right here. Yep. That's Tau Tauri. Tau, not T.
Okay.
T Tauri is in that nebula, remember? The what nebula was that we were looking at? Heinz Variable Nebula, is that it? Does that have the T Tauri prototype star in it?
I don't remember. I have to look.
It's one of those. Well, this is Tau, so it's not T. It's a different star.
Okay.
Let's just clear this now and see where we are. And Cosmic Ray is with us, I guess. I didn't see that. Hello, Cosmic Ray. Yeah, look at this. That's pretty cool. Remember the two stars were almost in a direct line with this nucleus? Now look. Now if we draw a line through these two stars. See that? We did this last time and this part was touching that line. And now it isn't. We haven't changed anything in terms of the adjustment. So you can see the dynamic universe changing right before your eyes. I think that's really cool. Okay. All right, let's go back to looking at it with its nice, beautiful, expansive coma of carbon molecules and cyanogen. Hey, David Galich, thank you for the contribution. It's very kind. The cyanogen molecule will many times appear in pairs, so you have a CN and a CN. Okay, and they're going to be all linked together courtesy of those carbon atoms that are so easily bonding to each other and to other things. It's actually quite interesting. Okay, so absolutely beautiful. You know, the comet is always fun to look at. You know, I was thinking we should actually go check out something else while we're here.
Yes.
Yeah, it's literally right over here. Right there. And I think we're going to go there. And we'll also look at the Medusa Nebula one more time, because I'd like to pursue getting a nice shot of the Medusa Nebula. But first, before I do that, I'm going to save what we have for our comet. Because I think that's kind of cool. Oops, that's a long letter. There we go. So we're going to save this, and you'll see up there it says it's saved as a FITS file, and I'll tell you what that is in a sec. And then save exactly as seen. That's a PNG file. You can double click on that and see it. Now, where would you do that? You'd go to skytourlive.org, all right down below me, and you would scroll down to the next section, which I think is in gray, and it says take me to cool pictures, and there's some instructions right there what you do when you go to our website, and you'll be able to see these files and see exactly what we do, and they'll be there in seconds. All right. In fact, the Comet probably is already on its way up there now as we speak, and will be available in just short order. So skytourlive.org. When you go to skytourlive.org, as I've said many times, to the upper left, you'll see SkyTour LiveStream, which takes you to this stream right here. But to the upper right, you'll see the Patreon, which is our subscription Patreon that we have for SkyTour LiveStream. We have several tiers. We have a number of people that are patrons right now, and we've just started it, so it's taking on a life of its own, slowly but surely. We respect and are happy with our patrons. We love them. Here they are. In fact, I only have a few right now, but the ones we have are right here. We have John P. We have Izabela. We have Ollie B. Chief McCyber, Vera Lucia Campos, Ronald T., Martin W., and Raymond B. so far. And that list should keep climbing, and I want to give them all shout outs and say thank you for your patronage. As a $10 a month tier member, you get access to 4 of our highly processed, highly finished images each month, and that's a special directory you can go to, download these very, very large resolution images, do with them what you will, other than can't sell them, but you can just download them and put them on your desktop backgrounds, put them onto mugs if you want to, and so forth. So you can do that. For higher tiers, you can actually get access to all of our imagery that we produce like that, and there's over 30 photos currently in the total shot list right now, and that's climbing. And we have spent a lot of time building these objects up for you and making them just spectacular. And if you see any of the Facebook postings that I do, you can see an occasional very high-res image, which of course you can download from there too, but why not get all of them, if you want. Anyway, you'll see them there, but check out skytourlive.org. And if you haven't yet, do subscribe, hang out with us, be part of this SkyTour family. We have one active telescope right now, and I have one behind me that we're going to have active again as soon as we rebuild the building. Okay, I will show you that background right now. There's a telescope right behind me. That's actually the SkyTour East telescope. It's a 10-inch unit with a 5-inch refractor on it, and that will have cameras to show you the universe from here in Connecticut. And then out in Arizona, we have the one out in the desert right now, soon to be joined by a second one out in the desert, we think. And that means we'll have a total of 3 telescopes. So there will be no excuse for not being able to stream on a clear night. And hopefully, at some point in the future, we'll have a 4th telescope or more in the southern hemisphere. We're looking for a southern hemisphere spot as well, down in Australia in particular. So we'll see. We're ambitious, but you know what? Science is worth it, isn't it? Isn't it crazy? Cosmic Ray asks if anyone's done a spectrum of this comet. We have the capability of doing a spectrum of this comet. I just don't have it hooked up. That's for the telescope you saw behind me. That's going to have a spectrometer on it. So we would actually be able to see the cyanogen lines in this comet, the emission lines. So that'd be pretty cool. So you'd be able to see what cyanogen looks like, what carbon molecules look like. Pretty neat. We'd see the ionized emissions. Okay. All right, so let's save this right now. This is actually a lot of frames saved. We'll save it exactly as seen. Right, then we're going to clear it. So this is now saved. It's going up there. And now we're going to go and enter what I call our night vision mode. All right, so it's basically a 1 second exposure where we maximize the view. And that's why it's called night vision, because it looks like it's green, right? And we'll take out our object name. We don't need that right now. Okay, so let's go and over to our planetarium view again. And from there, we're going to go just down here. And this is an amazing location because it's the Crab Nebula. It is a remnant of a star that blew up. That star was seen in 1054 AD when it exploded. It was seen by Chinese astronomers, and it was even seen during the day. And it was so bright that the star itself could be seen during the daytime, at least temporarily. And there it is. And as we start taking some imagery of it, several things happen here in rapid succession. What we do is when we come in here and start, before we take images, we have a guiding telescope, which is on the back of this telescope. You can't really see it. It's out of view right here. And the telescope is picking a star to guide on. All right, so we're going to center this up just about here. All right. And you'll see it's searching. It takes about between 11 and 14 seconds to find a guide star. And when it does, it then proceeds to start guiding. You'll see the numbers show up right there. Now it's guiding on this object. So now we can actually take a long exposure and it will not be blurry because the telescope is going to be perfectly guided. So we're going to take a 35-second shot of this object. That means for 35 seconds, we're going to let light fall on the sensor. And I won't do it while we are in this mode, this green mode, because we're going to have too much data and it'll make a bright white shot that won't look very pretty. But we're going to live stack it. So we're going to take one image at 35 seconds, then another image, align it with the first, and stack it. And we make this image sandwich, which will make all the subtle detail rise to the top, and the noise will fall away to the side, because every sensor has noise on it. So here in just 2 seconds, 1 second, 0. All right, boom. There's the Crab Nebula. Now let's actually process that a little and color correct. Look at that. So we'll move this up a little bit. Okay. Now if we zoom into this, you can, even though we only have one frame stacked right now, you can actually see that there are filaments and structures in here that are just incredible. And that's what we're seeing. And you're also going to see something else here in just a second. In fact, it's visible now, but not as good as it could be. All right, if I do this, it'll show up a little better. Okay, right there, all right, you can see, in fact, I'll point to it for you. It's right there. See that little tiny star in there? That's called a neutron star. That's the remnant of the stellar explosion. And that star is actually only about the size of Manhattan Island. And this is several thousand, about 6,000 light years away from us. And it's actually visible because it's so bright. All right. Now, it's also very, very hot. It's sending off most of its light in the ultraviolet, which is ionizing this gas. What is this gas? This is the gas that was the envelope of the star, that made up the star. It was the whole star. The core is highly compressed now because it's basically all neutrons. And there's several points when a massive star, during its collapse, it can become a neutron star where most of the surface is neutrons. And they're packed so tightly together that nothing can crush them further beyond a certain mass, all right, or up to a certain mass. And so they push back. And so they hold up the star, but they're highly, highly compressed. So these stars tend to be spinning very rapidly, like an ice skater pulling the arms in. They start to spin rapidly. Same thing happens to stars. And when we look at this star, the way this is doing this now, the way this is actually happening, this particular star is spinning at an amazing rate of 33 times per second. Imagine a star the size of Manhattan Island rotating at 33 times per second. Per second now. And it stays together. But it's a piker. It's an amateur when it comes to spinning rapid neutron stars. This one's also a pulsar. It has hot spots which are flashing us 33 times per second as it spins. Pulsars, being rapid rotators, break records all over the place. And there's one that spins over 700 times per second. Think about that. An object the size of Manhattan spinning as a sphere 700 plus times per second. I think it's like 715 or something like that. But we see it. And the colors are due to ionization of hydrogen gas, like here, oxygen, like here. It makes these beautiful colors. And so it's really pretty. We can actually enhance the colors a little bit. So that's a little more enhancement. So you can see more of the green and more of the oxygen green and more of the hydrogen, neon, and other elements. That's pretty, Daryl.
It is.
Look at that. Wonderful.
Interesting to look at that and contemplate. When it came apart, when it exploded, it looks like the hydrogen went some ways and the oxygen went other ways.
Yeah, and we can't see this in 3 dimensions. We don't know. This could actually be coming toward us. That stuff could be going away from us. I don't have a velocity map of the gas. I think there was probably one done, so we could actually kind of get an idea of how that's working, which way is which. So, the density of the material on this side, if this is coming toward us right here, this stuff, we might tend to see more oxygen. And then, if there's hydrogen in here, maybe it's masked by the oxygen and we don't see it because we see some here. There is some here poking through. It's all throughout this. I don't know. I'd have to see. It's really cool. Hey, Michael Hedrick, how you doing?
Well, I know, we see the similar thing with other supernova remnants, like the veil, for instance.
Yeah.
You'll see filaments. Some are red and some are blue-green.
Yep. Yeah. Interesting how that works, I'm going to do one more thing here, guys. I'm going to actually add an enhancement. I'm going to sharpen up those filaments for you. You ready? Okay, watch these filaments now. Watch this. Here we go. There it is. Look at that. Now you can see them much clearer. That's really pretty. Look at that. Holy cow. Look at that one green filament going through.
Yeah.
That's really nice. And all I did was I enhanced the color here. I actually did more saturation. We can actually reduce that and show you what it would look like if it was actually in black and white. That's what it would look like in black and white. Aren't you guys glad I have a color camera? Okay. Yeah, that's black and white. That's how I used to take pictures of this thing. All right, well, now we can actually see pictures of it in color. And you'll also notice the stars. The stars are different colors as well. Wow, this is nice. This is really pretty.
It is.
Okay, we're going to... All right, and this is an SNR, supernova remnant. SNR is the nomenclature that we use. All right, let me grab this. are. Okay, let's put that out there now. This is what we're looking at. Again, SNR stands for supernova remnant. This is almost directly overhead, as you can see by the telescope looking up there. So we actually have one of the finer views of the Crab Nebula right now. Nice. Robert Waters says, when Mars was at closest approach many moons ago, I manned one of the scopes at our astronomy club and cheated by using a red filter. That's actually not cheating. You know, we use different filters. I'm using filters right now. We could take a picture of the Crab Nebula looking just like this, you know, with our special filter during a full moon when there's so much light in the sky. And so it's not cheating. It's actually being smart. All right. So Robert, that was smart, not cheating. Hey there, Uberku.
I bought a Mars filter.
Yeah.
For the opposition a couple of years ago.
Uh-huh.
And it was a visual filter, but it was hot pink in color.
Wow.
And it was supposed to accentuate the dark areas on Mars.
Yeah.
But that hot pink was so glaring, it hurt to look at Mars through that filter.
And when you looked at other things, it probably changed the colors you saw.
Oh, I would take it out. I mean, it was interesting, and it did show the dark features on the planet, but it was like staring into a black light from about a foot away.
Oh, that's not good.
Just a really uncomfortable look through.
Yeah. I'm going to do something here, guys. I'm going to spread out the data down below here and move us over to see the entire curve. And then I'm going to move us down here. I'm going to take this entry. I'm going to move it down more and try and pull out more detail. Okay. So by coming here, yes, it's dimmer, but notice you can see the pulsar in the middle. If you notice the color, you'll notice it's kind of bluish. It's very hot. And these stars are very hot and blue. Okay. Asher Real is with us. Hi, Asher. You know? So that's what happens with neutron stars. They're very, very hot and blue. Okay, let's go back to bringing us back to this beautiful view. I'm going to come off the zoom here for now. All right. I do actually kind of like pulling this down just enough to be able to see that star in there, because that actually is the primary element inside this nebula, which makes it so interesting, is that star.
That star, the neutron star, is the kind that they say if you took a tablespoon of it, it would weigh like millions or a billion tons.
On Earth, yeah.
On Earth.
Yeah. That's how much compression there is, yeah.
Yeah, the part they don't tell you is if you took that tablespoon of neutronium into Earth's gravity, it would promptly disassociate violently, but without the gravity to keep holding it together at the star.
That's right.
It would dissociate violently, and you would wind up with one great big kaboom.
Yeah.
Big bada boom.
Yeah. There's a lot of energy stored up in that compression, because it's the overall gravity of all the mass that's holding all that material together. All right. And if you did try to take a teaspoon away from the star, well, first of all, you'd have to be able to dig into the star to grab it. And of course, if you could figure out some way to do that, you wouldn't be able to hold it cohesive. As soon as it left that gravitational field, which would be maybe a matter of just inches away from its current position at that point, it would just, as Daryl says, completely disassociate, explode, and then, of course, rain back down on the neutron star and take you with it.
Yep.
Okay, this is great. This is 21 here. We're going to pause this. We have Crab Nebula there. We're going to save it. All right. And the FITS file is the astronomical format, and that's for people that want to actually go and they can take that down freely. That's for you if you want to process it yourself to make it look like this. Otherwise, if you want just this, that's what the ping file is. So if I click on this, right, this is what you get when you go to our database minus this. Let me pull this out of there. That you're not going to see that there, but you're going to see this, all right? And you could zoom in on it. You can move it around. You can see the pulsar and have a lot of fun and just go digging through all the objects we have up there, right? And that's for you. That's for you guys to be able to do if you want. Okay,
Can we zoom in on that a little before we go?
Yeah. I'm glad you asked. I was about to clear it. Okay, we're at 183% of our sensor right now, so it's looking a little fuzzy. But that's really pretty. We're seeing a lot of good spindle structure in here.
Yeah. There's a little fuzzy feature just to the right of the neutron star.
I mean this? This guy
Yes.
right here, yeah. Yep, right there. And again, notice the neutron star here. It actually looks a little bit blue. And that's something that is really important because that blue color you see right there, all right, for that star, that blue color is really what a neutron star would look like. It would be this really, really brilliant blue color because that means it's extremely hot. Even though it happened, you know, in 1054 AD, okay, this star will be that hot for billions of years. Because if you think about it, there's no real cooling mechanism other than radiation. It has to radiate away that heat. And as it radiates away the heat becomes less, but it takes billions of years for that heat and radiation to wane to the point where the star will even change color. And that spinning does slow down over time, but it's still it's going to be spinning at the same rate for many millions of years anyway, and it'll be slightly different in a billion years, and beyond that it'll be different. But I don't think there's any pulsars we've seen in the universe that have spun down at all. I don't think there's a single one out there that we've seen spin down. They're all spinning very rapidly. Again, not much to slow them down except tidal forces and interactions with their own material that is surrounding them. All right. Well, that was a beautiful object, guys. Thank you for hanging with us for that. And we're going to go back to our night vision mode here and bring this up to show you what it looks like, yeah, kind of in a telescope of any size. It would kind of look like this. You know, that's sort of what it would look like. All right, let's see here. I'm waiting for our internet connection to come back. There we go. We are using Starlink, and Starlink has growing pains. I mean, SpaceX does have some coverage gaps, and we have 99%. See, that's what I was talking about. We have 99% uptime out there, but that 1%, it shows up in a few seconds here, a few seconds there. 95% right now. So there it is. That's what it would look like in a relatively big telescope. In a telescope that's not so big, it might look a little more like what I'll show you here. If you looked at it, say in a 8-inch telescope, let's see, not there. Sorry. It might look like this, where you see a little fuzziness like that. Right, but those those spikes and the beautiful filaments, yeah, you don't see that unless you're actually in a very, very powerful system and a big telescope. All right. So let's go back to here. And let's go. What is this guy? Oh, I know what that is. We're not going to do that now. But I will do another object that we looked at the other day, which is quickly becoming one of our favorites. And it would be this one right here. This is called the Medusa Nebula. And I think we'll be able to see it right now. And the only reason we wouldn't is because this part of the building would be in the way. Because it's going to look over that way. There it goes. Well, we got it. Alright, and the Medusa Nebula is right here. You can see it. There's a fuzzy little spot right there. Okay. Alright, so what we're going to do is head west. Pull it into the center of the view a little bit. Okay. And then just pop north a tiny bit. Alright. Hey, Bullwinkle. How are you? Hey, Rocky, watch me pull a rabbit out of my hat. Again, that trick never works. Alright. Alright, we're searching, we're calibrating, and there we go. We're guiding now. And now the Medusa Nebula, ladies and gentlemen. We'll let it stabilize. The Medusa Nebula is actually a planetary nebula, meaning it's the remnant not of a supernova like the Crab Nebula, but the result of a star that has expanded into a red giant and undergone these thermal pulses when it reaches a special time in its evolution where it's unstably fusing helium into carbon and hydrogen into helium in shells around the nucleus, around the core, and that makes it unstable, so it puffs. And every now and then, every 10,000 years or so, or even 100,000 years, you might get these puffs, and you might get 7 to 10 puffs, and they send these concentric shells off of the star of material. Sometimes it's not exactly lined up with the star, sometimes it is. This one is not, but I'll show you. Let me actually go through this. I'm going to do a let's do tonight it'll support it. We're going to do a 50-second shot of this, and that 50-second shot will allow us to see other details that we haven't that we've missed before. Our sensitivity is at 300. Our telescope system goes to 600 sensitivity on the sensor, and of course 50 seconds at 300, a nice average shot. And again, this down here is this yellow bar way over there. Okay, if we come over here, that yellow bar right there, that's our progress bar right here. And you watch that progress bar when it fills up. If you can read the numbers, you'll actually see the numbers showing you when it's about to be done, and that's actually in just a few seconds. The first shot will be here in 3 seconds. All right, so here we go. Okay, boom, the first shot. There it is. Look at that. That's beautiful. Oh, really nice. And we can show you already because this is an extremely showy planetary nebula or stellar remnant. There's a star in here that's very obviously the central star. We looked at it the other night, and I called it out and said, I think this is the one. And it turned out we were looking at the correct central star. If you look, you wait for another shot to come in, and it will certainly make it show up very brightly. You look in here, and you'll see there's a blue star, very blue star. Okay, that blue star is actually the central star of the planetary nebula. Now, unlike the Crab Nebula, where that blue star was a pulsar and a neutron star, this blue star is a white dwarf. Why do we call them a blue dwarf? They are hot and they are blue. Most of their light at 30 to 40,000 Kelvin in temperature is being given off in the ultraviolet and causing this gas to be ionized. That's gas being red hydrogen, and this greenish blue stuff being the oxygen. But again, that's simply because the star is so hot it's ionizing this material. Okay, but you can't miss that blue star right there in the middle. Can't miss it. Right there.
When we looked at the crab,
Yep.
Classic example of a supernova remnant, this is called a planetary nebula, which is an order of magnitude milder than a supernova. The star didn't have the mass or the energy to go supernova, so it just went to white dwarf stage, and instead of exploding violently and blowing all the material off of it, as in the Crab Nebula, when the white dwarf was still a star, it got old and turned into a red giant or supergiant and puffed off its outer atmospheres. Just kind of gently puffed and blew away the step you see here instead of violently exploding it away.
Yeah, that's what I was saying before about how they reach a point in revolution where they're fusing helium into carbon and a shell around the core, and hydrogen into helium and a shell around the core. But that's unstable, and it makes the star thermally pulse, and then it does that puffing, which is what I was talking about. And that puffing will cause this to do exactly this. So we end up with these beautiful, I just color corrected, it shows up nicer. And it will cause these concentric shells to come off, but they don't come off evenly sometimes, or it looks like they don't, and that's because what they're coming off into may not be the same density or lack of density. So on this side, for instance, there's a lot of stuff that was probably hitting other material. On this side, there wasn't much for it to hit, so it just kept going. So they could be oblong in shape. They could be oddly shaped because of the density of the material around the star already that would be caused by other things. Like if there's dark nebula in here, those are actual particles. Well, if hot gas hits those particles, it's going to slow down the hot gas as it moves outward. And the different shapes that you see in here could be due to electrical interactions in these long filaments that are like a light year or two in size. So that's a planetary nebulae are well understood for being lesser understood. They're actually mysterious, and now we don't know whether certain other stars may actually be the stars in the middle of planetary nebulae, and those stars are called Wolf-Rayet stars. We don't know. There's a possibility, and we have to look at the similarities, because there are crossovers between how those very hot stars, which tend to blow off their outer layers and will become supernovae someday, react compared to these stars, which might be white dwarfs in the middle, which are done reacting. We've never visited these stars. Oh, this is looking nice, though. This is really pretty.
Looks like a chili pepper.
Yeah, you said that. It does, doesn't it?
Yeah.
Let's see if we can. Let's see what else is here. So we're gonna bring this guy and give it just a little more background. Now you can see there's more stuff out here. That's what I was talking about. It's unevenly distributed. You'll also notice that there seems to be some red cast to everything in here. That's because there is diffuse hydrogen gas throughout here that has nothing to do with the star. That's the bed of material within which this star proceeded to die. So it's pretty interesting. Okay, so we can bring that back down, because there we go. What a beautiful location. Well, it's a beautiful location, but it certainly wouldn't be healthy for us, that's for sure. See if we can zoom in more. See what we get. Now, if there's any doubt as to which star is the actual progenitor or culprit, well, there it is. You can't miss it. Right there, that blue star. These are all field stars.
That's striking right there.
It is. I'm going to remove some of the noise here. Look at that. Wow. You know, in the summer we look at the Dumbbell Nebula, we look at the Ring Nebula, and I look at this and I say, wow, this to me is a new favorite. It really is.
Yes.
I see Mike has a question here.
I agree.
Do we have examples of nebula interacting with other nebula? Oh yes, we do actually. You might be looking at one right now. This might be interacting with other material out here. There's diffuse nebulae here, hydrogen gas. This one's not very obvious. One that is obvious, though, is the Bubble Nebula. The Bubble Nebula is one that's a Wolf-Rayet star, one of these stars that's blown off its outer layers, and it's interacting with another nebula around it. Okay, and it actually could have created both nebulae, but the stuff blowing off is interacting and snowplowing into other material that's just to the left side of it. And we can't see the bubble now. It's not up high enough for us to see at the moment. But that is an example of a nebula interacting with another. Another one that we can look at is the Running Man Nebula. That's
I was about to say.
Were you about to say that? Okay.
Yeah.
The Running Man is an emission nebula, that is to say, a hydrogen region that's interacting with dust and causing the dust, in fact, to glow with the sorry, not the dust to glow, but the hydrogen gas to glow with the red emission nebula that hydrogen does, and then the stars that are causing that hydrogen emission are also having their light scattered by the dust particles as well that are in that area. So you see a emission nebula inside of a blue nebula. And the way light works, the nebula is blue and the emission nebula is red, but the red is trapped inside this blue nebula. So what we see for the light getting out is magenta in color. And that's really cool. Okay, we have 11 here. We're going to go to a dozen of these, and then we'll move on. Maybe we can actually go to the Running Man right away and see what that looks like.
Seems logical.
Michael also asked, is it dense enough to cause chemical reactions in? Well, we're looking at an atomic reaction here, right? We're watching ionization take place. So, you know, and because of the nature of the dark cloud soup that this is all in the Orion region, there are other chemical reactions taking place. There's ice that is attaching to the dust particles. Those ices can be carbon monoxide, methanol ices, water ice, carbon dioxide ice, ammonia ice. Okay, and so molecules are made. That's a chemically, you know, there's chemical reactions going on that build molecules out in deep, dark, cold space. And when that happens, they attach themselves to the dust grains, and then stars, if they come into being, they will proceed to then heat those dust grains, and those ices will sublimate off, and now you got these loose molecules of ammonia and carbon monoxide and methanol and so forth. And those are the types of things that get swept up in planet making processes, and you end up with all these different elements that are made from countless supernova explosions that are now floating in that dark cloud as well. The calcium, the magnesium, the potassium, and so forth and so on. And all of that stuff goes into making up the planets that you might see. And it's so funny to think that there's just these tiniest and tiniest of atoms out there, but so many of them that they can form an entire planet, or never mind that, negate that, an entire solar system of bodies, which includes all the icy bodies of rock and so forth in the asteroid belt, this kind of gives you an idea of just how much of this material that we're looking at right here has been spread out into space in the billions of years since the formation of the universe. Really pretty. Okay, we'll do this one last one to go to 15. I didn't want to go to 12, and then we'll be good. What a beautiful nebula! This is really pretty.
It's blinking at me.
There is a blinking planetary.
Yeah, I mean, this one, the intensity seems to be cycling back and forth.
Oh, I did just change it. I just brought this down. Now I'll bring it back up, and it'll look like it's going brighter.
Well, it was doing it earlier too.
Okay. All right, so we're gonna save this now. Okay. And now I'm gonna bring this back down and save it exactly as seen. Shoot, I saved it in the Crab Nebula folder. I'm gonna rename it. My mistake. Okay. And this is the Medusa Nebula. It's a PN, planetary nebula. It'll complain and tell me that I've got to rename the stack. Yes. Which is fine. If there's any problem up there, I will fix it. Alright, so now we can save it again. Hey, it's a benefit. We got an additional shot. Okay, so now we have a FITS file up there, and we'll save that exactly as seen.
The blue of the white dwarf is very striking in this image.
It is. It is. Well, keep in mind, I did increase the color saturation. But I wanted to because this helps see this stuff much, much better. Alright, so we're going to get out of this now. Go back to our night vision mode. And from our night vision mode, we'll pop back to our overall view, and then come back to our telescope planetarium mode and get us to a new object. And we will not see that. Okay, we'll rename this. Let me just. Yeah, that's fine. Okay, good. See, that's all the stuff on its way up to the server up there for you guys. Okay. Now we're gonna go to the object that we were just talking about. That's the Running Man. I think that's NGC 1975. We're gonna find out. I don't remember. Probably is. Oh, 1973. My mistake. It's right above the Orion Nebula. So the telescope's gonna swing around and actually start pointing toward us. Alright, so let's go back here and get that to happen. Zoom in. Yeah, there you go. Our images are actually better than the Stellarium images. Okay. Here we go. There's the Orion Nebula, and there's the Running Man Nebula. This is just beautiful. It's a very, very dense region of dust and gas. So we're going to come up just a little bit so you can see the Orion Nebula as well. Also known as Messier 42. And Messier 42 extends so much further than the parameters of this below area. So, but we're going to do the Running Man now.
Michael has yet another question for you.
I like he has lots of questions. That's cool. What did he ask? Just let me know if you could.
He says, what is the percentage of OBAFGKM stars in each category on average in our galaxy?
Excellent. That's a good question. Okay.
I can say one thing.
Okay.
I'll let you answer it, but Michael, I'll give you a hint. There's far more of one of those than there are the others.
Well, that's true. Michael, you know, the O and the B stars are the brightest stars. They also live the shortest amount of time. The O stars live on average maybe between 5 and 12 million years before they go supernova. Maybe a little longer. The B stars a little longer, but they go supernova at the end. And the total number of those that in the total galaxy is about 2%. Okay, the vast majority of the stars in our galaxy, in fact, in the entire universe, are the stars at the very, very far other end of the spectrum, the scale there, and that's the M stars. They're the coolest stars, as in the lowest temperature. They're also pretty cool, okay, but they're the lowest in temperature, and they are very, very well, active. Okay, they have they're usually called flare stars. They have many high-end flares that would you would tend to think they might sterilize a planet going around them, but if a planet has a dense enough atmosphere, it may not have been completely wiped out, and so there's more planets around these M stars than any other type of planet. I'm sorry, any other type of star there is. And part of that's because most of these stars will tend to have a number of planets around them. But keep in mind that because they're only about a hundredth as bright as our sun, and about the same smaller, okay, a hundredth smaller, it's actually better to talk about them in terms of Jupiter's orbit with Jupiter with its moons than to talk about it with the sun and its planets, because it's on that scale within which they actually reside, and the characteristics can be described best. Okay, so example, TRAPPIST-1. TRAPPIST-1 has a number. Oh, it's beautiful. Has a number of a number of planets around it. And every one of them, there's like 7 different planets around it. Every one of those planets is closer to the star than Mercury is far from the sun. Right? Within the orbit of Mercury distance. And 3 of them are actually in the habitable zone. So Mercury's surface is so hot that lead would melt. Yet around this particular star, this TRAPPIST-1 star, we find that we literally have a situation where it's so much less luminous and so much less hot than our sun. Our sun's around 5,000 to 7,000 Kelvin at the surface, and these are between 2,500 and 3,500 Kelvin at the surface. So at that point, what you're looking at is a star that's big in your sky, but isn't producing a lot of radiation to strike the planet and make it warm unless it's close to the star. And that's what that's why M stars have the most number of planets, and because they're the most copious star in the universe. But one thing that's very important to understand is that because these stars are so small and the planets so close, the planets tend to be tidally locked. So like the moon, they have one face always facing the star. So most likely, life would arise depending on how far they are, either on just the sunlit side or just on the terminator, just on the side where there's like a band heading into the cold, dark other side. And if the atmosphere was thick enough, it could transport enough heat to the backside so that maybe life of different forms could exist on the bright side, the perpetual sunset side, and the dark side. Interesting stuff. This is the Running Man Nebula right here. You'll notice that as promised, the emission nebula in its center is magenta in color. Look at that. Isn't that cool? And this is brown dust that's sitting in front of this nebula. All right. And this entire region is part of a gigantic molecular cloud complex, which I know Daryl was just thinking and probably was going to say. Sorry, I bet you were going to say that. The OMCC, or the Orion Molecular Cloud Complex, is an area where, as I said before, we have a lot of this dark dust. And this dark dust is actually a place where ice is formed. These dark particles are the progenitors of planets. And there's a lot of hydrogen gas in here. So this hydrogen gas will form new stars, such as happened here in this location where there's a lot of gas and dust. And there are 4 bright stars in here called the Trapezium that are overblown in the center because they're so bright. And these 4 stars, among others, are responsible for lighting up this nebula by ionizing the gas and making it glow. All right. Out of this, we'd get an emission spectrum out of here. Okay, we'd see bright lines in our spectrum. Okay, and so this is an area where it's just emission spectra. And this blue area, this is actually scattered reflected light, okay, from the tiny dust grains, of which you see here. These are brown grains of dust that are not taking part in the reflection, but they're being silhouetted and just mildly illuminated by the other nebulae in the region. It's really beautiful. We always take pictures of the Running Man in the winter. That's really pretty. Let's zoom in. Daryl, I don't see your Baby Ruth Bill Murray here.
The exposure has to be turned way down.
Let's drop the color a little bit. Reduce the brightness. Maybe a little down lower. Does that help at all?
A little. I can barely start to see the profile of his face and his mouth. It's overexposed again now.
Okay. Well, we are doing a 35-second exposure, so that's kind of tough.
Oh well.
All right. Let's see what it wants to do.
Excuse me, please.
Yep. Okay, so we're getting this beautiful brown dust showing up very, very beautifully here. That's nice. And if you actually wonder what's actually going on here, all you have to do, we can actually show you what else is here by doing this. All right, so now we actually pick out much more of this detail in here. Isn't that amazing? Hello, Donald Kunzer. I don't think I said hi to you. Cosmic Ray, do you not like the fact that we imaged the Orion Nebula multiple times? That's nice. Look at that. You can see this subtle detail out here. Sooner or later, someone's going to come back and look at our data, and they're going to look at the image we did of the Orion and Running Man complex, and then look at it a year later and say, holy cow, a star winked on. They might make a discovery, an astronomical discovery. And that's why we make this stuff publicly available. So in case anyone wants to do that, they might be able to see a difference between the Running Man Nebula and these two nebulas over time. And so unless we take multiple images, we'll never be able to do that. This way we make it available for all of you to do this if you want. It's actually kind of cool. Really pretty. That's beautiful. Wow. Okay, we got 14. We're going to go to 15 and stop on this. So it's in 4 seconds. And that'll be up there for you to see, take down, and use, and have fun with. Okay, that's really pretty. That's right. Ray says, discover new things. Exactly. The only way to discover new things is if you look at objects over and over and then look at them and see the differences between the last shot and the next shot. That's what happens. That's the best way. If a star winked on, you'll see it. You'll see it in a 10-second shot versus a 15-second shot, or a 30-second shot versus a 35-second shot. We stick around those times so you can actually be able to do that. There you go. Okay. So we've saved it exactly as seen. So it won't let me do it again because it's out there already. So we'll go back to that. All right. So we'll go back to our... it's just beautiful, isn't it? Man, that's nice. That'll be up there in just a few seconds. Let's take a look down here. Let's bring this up. I'll show you why. Okay. Let's zoom in here. It did this 1 second shot here. And there are those 4 stars I was telling you about. Let's go down here and take this imaging down to make it a little bit less of an object brightness, and now a little higher so we can see the object. Actually, we're gonna increase the brightness here just a bit, catch it a little more. Okay, and I can see that we want to refocus here. So we're going to do that. We're going to refocus. We're going to go up to here. And we'll refocus. Let me zoom out. Doesn't matter. It's doing the entire camera view, not just what we see. A little bit out of focus. I have to put on my... put on the other... temperature control. All right, so we're gonna take us out, and then we'll scan in and do the focus again. As the temperature... Oh, go ahead, I'm sorry.
Was your T comp off?
Yeah, it was. I had focused about 45 minutes ago, and the temperature dropped, and my mistake. I should have had it on. Yes, Ray, that's what I'm going to do. Actually, after he has to show people what they'll see in the backyard scope. Fish mouth with 4 stars in the trapezium. Yep, that's where I'm going with this. And once we get our focus again, you'll see those pinpoint stars in the trapezium.
The fish's mouth makes Bill Murray eating the baby Ruth.
This guy here?
Yeah.
Okay. Okay, there's our focus. Let's go to best focus. And then we can get out of this and zoom in, and there we go. All right.
The dark feature to the left of the trapezium is people used to call it the fish's mouth because it kind of looked like a fish with its mouth open.
Yeah. Okay. So there's the trapezium right there, but let's reduce the gain. Use that as our controlling factor. Well, there you can see the 4 stars in the trapezium now. Called the trapezium because of the shape of these 4 stars. It kind of looks like a trapezoid. Okay.
It does?
Yes, it does.
I thought it looked like a trapeze.
No, a trapezoid.
Trapeze.
Okay.
I'm pulling your leg. It's a small joke. It's a very small joke.
Well, I was trying to imagine a trapeze somehow, and I was having trouble seeing it, so I was wondering, is there something I haven't heard? It's all right. It was funny. Okay, so that's the trapezium. So now, depending on how big your telescope is, you'll see more than this. But generally, what you see, I'll show you as we'll move up the gain ladder here. Okay. In a bigger telescope, you'll see something. Let me zoom out a little. You'll see more than this. And what you'll see is probably, you'll see these wings in the nebula. Okay, for sure. And then as we increase the gain, you'll be able to simulate what a bigger telescope will see. The one thing you won't see though is this color. You're not going to see the color. Okay, the color is unfortunately very subtle, and your eyes are not tuned to be able to see it. You know, you'll see it. You'll see green because when we take images of it, you'll see it looking green, and so you might see it as green. All right. So what we'll do now is from here, I'm going to get us to about there, and I'm going to move us down a little bit and put the Orion Nebula right near the top. Okay, right about there. Okay. And then we're going to go to a 35-second exposure again. After we find our guide star, we'll commence that. There we go. All right. And we'll go into our stack again. And remove this previous one. And this one will link right up to it. It'll be a mosaic. And we have 12 seconds left, as you can see over here. By the time you look at it, it'll say 5 seconds left. All right. And you'll see more of this Orion molecular cloud complex down below here, which will start to show up as soon as we pull this stuff in here. So let's move this out a little. You can start to see more stuff down here, and we have a little further to go, but we'll be fine right here. Notice all the dust down here. It's a tremendous amount of dust. Let's see what's really here. See that? You can see how much dust is here. And we're right at the border of another object that's beautiful to look at. It's called the Rubber Stamp Nebula. I believe it's NGC 1977. New General Catalog Number is the object. Beautiful. There it is. Yep. Okay. All right. I'll make this dark and try to bring out more detail. So as you can see, there's a lot of dust in space. A lot. You know, this guy down here, this is a beautiful reflection nebula, blue, and it's shining through dust that's right here, but there's other clouds that it's reflecting, that are reflecting its light from the star down below it and behind this other cloud. So this is the 3D universe right here you're seeing in action right here. Look at this. Looks like actual clouds, but that's actually ionized oxygen. Doubly ionized oxygen here. The purple halo, that's an artifact of our system because it's so fast photographically. Yes, Izabela. This is a mosaic. We will be going back to the Comet after. Daryl, if you've got any objects you'd like to see, let me know, and we'll go there too.
Okay. Keep thinking positive there, Ray.
Is it April 8th, 2024?
Yes. The big solar eclipse next year.
Oh, that's right. Well, Ray, we have an expedition planned, so of course it's going to be cloudy.
You know, as a general thing, the farther east and the farther north, the prospects for bad weather are worse.
Yeah.
I lucked out with the one back in 2017. I lucked out on 2 or 3 counts.
Mm-hmm.
It was my sister and her husband were observing from southeastern Nebraska.
Mm-hmm.
And they were totally clouded out. And I saw it from northwest Nebraska, and actually when I first got to Scotts Bluff, it was cloudy there.
Wow.
And a lot of that was it was morning, you know, humidity and clouds, and it cleared magically. I remember I drove right over the North Platte River, and as soon as I got out of the river bottom, it started clearing up and turned into a beautiful clear day by the time I got to north of Scottsbluff.
Wow, very nice. I want to say hello to Jennifer Miko. Hello, Jen. I want to say hello to Rosanea Trajano. How are you? And Robert Fraccia. Unless I got Fraccia. Let me know if I said that right, Robert. Well, how are you guys? And make sure you subscribe if you haven't yet, because it's lots to see here. Daisy and Zoe, hello to you guys as well. Don't worry about being late. Look what you're getting to see now. Look at that. It's beautiful. Yeah, we'll see if we get to see the eclipse next year. We do, we do. If we don't, we don't. It'll still get dark. You'll say, darn it, behind those clouds up there somewhere, you know, it'll be dark, and the birds will start, you know, going to sleep. And the bugs will start to sing. For about 4 or 5 minutes. Then they get, wait a minute, false alarm, guys. I thought night was coming too quick. Look at this. Holy cow. I just love all this dust that's in here. You just can't miss it. Let's pull this out of here. Like that. Maybe like just about like this. Let's pull this down too. Let's see what else is here. Look at that. There's a lot here. A lot of dust in there. Really pretty. Again, we're going to go to 15 frames to match it with the first. Robert, is it Frachia or Frashia? Did I get it right there? Jose Santos, how are you? Thank you for coming out. Make sure you guys subscribe, okay, if you haven't yet. Hello, D. D. Smith is with us. Nice to see you, as always. And Michael Hedrick has a question for you, Daryl, about the eclipse and what it looks like from Hubble. What it may look like from James Webb and Hubble.
Sorry, I was looking something up.
That's okay. Because we kind of know the answer.
Michael, they would never point the telescopes, if you mean neither telescope would they ever point toward the sun. The Webb is specifically designed to be permanently blocked from the sun.
Right.
You mean if they looked at Earth from the telescopes, with the eclipse happening across its face, neither telescope would do that either, but they have taken shots from space, other satellites, looking down on Earth when a solar eclipse passes, and what you see is just a big dark blotch on the face of the planet. It's not sharp-edged. The moon's shadow on the face of the Earth is actually rather small. Where the path of totality is, that is, the sun is completely blocked. Then there's a bigger, fainter shadow around it, which is where the sun is peeking out from around the edge of the moon.
Right.
So it just looks like a big patch of dark going across the face of the planet.
Yeah. And Jose Santos is in Portugal. Hi there, Jose. Thank you for watching from Lisbon. It's good to have you with us. Plus, the other thing, too, is the James Webb is 1 million miles away, and it might not see the eclipse, all right, at all, from its position. And it wouldn't certainly see the eclipse because it'd be on the other side of the location where it would possibly see it, even if it tried to point it at it. The Hubble is orbiting, so if the Hubble was to go on that side, it could see the shadow crossing the Earth if they pointed it at the Earth. But they would never do that because the Hubble's not designed to look at the Earth in the same way that other telescopes like Landsat telescopes and others, weather satellites, are designed to look at the Earth.
Well, you know, that's an interesting point right there, because the Hubble was derived from spy satellites whose express purpose was to look at the Earth.
Yep. But the optics are all different.
Yes, now they are.
Yeah. Okay, so we have saved this already, as I said, and okay, so that's good. So now we're going to go back, and this is interesting how we do this all the time. Okay, our night vision mode is here again. Okay. Do you have any other objects you'd like to see, Daryl? Because we could go to those right now.
Oh, well, while you're here, you ought to look at the Horsehead. You're close.
I am, yeah.
You know, the other one I'm going to say is the Boogeyman. It's not far
Oh,
away.
yeah. We could do the Boogeyman as well.
Boogeyman of Caspar.
Yeah. Boogeyman and Caspar on the opposite sides of the Barnard loop, actually. All right, so while tell you what, we're gonna look at the we'll go to the Horsehead right now and check it out, and then we're gonna we'll do a short set of exposures of the Horsehead.
Yeah.
Because we're gonna want to move up pretty quick. There's the Flame Nebula right there, and the Horsehead is down here. You'll see it in a second. We're actually going to this nebula right here that you'll see here shortly.
The Flame is the favorite of Daisy and Zoe, if I remember correctly.
Oh. Okay, well then what we're gonna do...
I'm sure we should get back and look at the Comet sometime.
Yeah, I mentioned we would, and so we will.
Yeah, probably why a lot of people are here.
Yeah, that's right. We're going to look at the Comet. Okay, so let's come back here. All right.
I learned something tonight.
What's that?
The Trapezium
Yeah.
was discovered by Galileo.
Oh, interesting. I didn't remember that. I think you're right. I think that's historical fact.
February 1617.
Wow.
He only saw 3 of them, though.
Yeah, that one on the upper right's a little fainter.
There are actually at least 8 stars in the Trapezium, and several of those are binaries.
Mm-hmm.
There's actually quite a little star cluster going on there.
Yeah.
The whole thing is only about 1.5 light years across or less.
Yeah. Very, very hot young stars.
Yeah.
Okay.
They are what's lighting up the enormous Orion Nebula.
Mm-hmm. Exactly. All right, let's all right, we're guiding now on this, and we'll do a 35-second shot of this, and we'll do just maybe 5 frames or so. We'll see. Here we go. We'll get rid of our last view, which is this beautiful... Yes, I know. No, I will fix that. Okay.
Whoops. Darn it, forgot something. Be right back.
Okay.
Just a sec.
No worry. So, you guys having a good time tonight? Oh, there we go. Look at that. Wow. Beautiful Horsehead Nebula. And there's the flame for Daisy and Zoe. Right there. Very nice. Yeah, these look beautiful. Let's see where it wants to go for processing. There we go. So you can see the details in here. It's almost three-dimensional. You're like falling into this hole. You know? As we get a few more exposures. It'll be beautiful. And zooming in on the Horsehead for a moment. you'll notice that the top of the Horsehead is illuminated, and there's a star right there. There's a star right there. There's a star right there. So we're catching all the bright stars that are in there rather nicely. And let's see, let's make it a little darker. You can see this beautiful area here.
Cygnus is what, or Cygnus. Sigma is what's actually illuminating the red cloud behind the Horsehead silhouette.
Right, and Sigma is right here.
There. And you could compare Sigma in a way to the Trapezium, because that's actually several stars all going around really tightly.
Yep.
Sigma's beautiful in the eyepiece.
Yep. Thank you, Papa Tom. He says we're really enjoying this tonight. Excellent. Thank you very much. The Horsehead Nebula, that black horsehead looking thing, that's actually also known as Barnard 33. Okay. And E. Barnard was an astronomer who cataloged a dark nebulae, which is what this is.
Barnard was a pioneer of astrophotography back in the late 1800s and early 1900s, I guess. That's how he managed to catch a lot of his objects, because they were too dark and dim to see.
Yeah. Then you can see, if we zoom out a little bit, you'll see that this is like a wall. Okay, this wall is the edge or part of the overall structure of the Orion molecular cloud complex, of which the Orion Nebula is part, the Running Man's part, and a lot of other nebulae in this region are a part. And that's what we're seeing here, is this wall. Now, to see what else is here, we can actually pump this up, and you can see that there's more structure out here. Okay, and this structure is, again, pretty amazing. Let me pull it back a little bit here, get to the point where we can see a little more detail. We're over processing right now just to show some details. All right, now that's a little over processed. Let's bring it back some more. Okay, so if you look right here, this line, you can see this line of material that's crossing in front of a reflection nebula, which is the blue part, of course. And that blue part right there is silhouetting this beautiful material that's crossing over it. And once you get these deep exposures, you can see that this material is literally in front of it. It's very cool. Michael, thank you for coming. Michael has to go cook. All right, cook something good, man. See you later. Donald Kunzer says there was an anime titled Dark Myth that had drawn the Horsehead. It had hand-drawn the Horsehead Nebula, and it was filled out as a column of dark cloud against the red. That's exactly what it is. It is a dark cloud against the red. Okay, let's pull this down a little bit.
Up to the
flame, yeah.
You know, when you had that, there you go. When you had the colors drawn back a little, like it was and it is now, you really get you can see the gradient.
Yeah.
Falling off into the flame.
Yeah, and the gradient that Daryl's talking about is how this is bright red here, and it falls and trails back into almost a golden pink in the backdrop. Again, we're seeing this in 3 dimensions. This nebula, this emission nebula, is inside the structure here. This is material that's between us, that's here, and the nebula is behind, back over here. Okay, so that's dust that's in front. It's not a void in the stars. That's stuff in front blocking your view of what's behind it. Okay, we see that a lot. Okay, the Horsehead is another example, right, where the Horsehead is material sticking out from the molecular cloud that is blocking the glow of this hydrogen emission caused by Sigma over here, this bright blue star that we talked about just a moment ago. All right, it's blocking it there, and this star here is having its light scattered by dust inside this area. All right, and so there's not a lot of hydrogen in here that the star can ionize, so we don't see a lot of it, but there is some. There's a little tiny bit right here. All right, so we do see some. So space is full of hydrogen mixed with dust in many cases like this in the galaxy. And if you look at this flame, many times people see the flame as just a shape that's, oh gosh, let me see if I can show that. The flame ends up looking, that's pretty. I mean, we actually, it's nice and pretty. We do have a fairly deep exposure, so I may not even be able to show it the way I want. There it is. This is what the flame might look like in a moderate telescope to your eye. But with a bigger telescope, or doing it the way we're doing it here, you can see a lot of detail. And that is quite a lot of detail, actually. That's probably the most detailed we've ever seen it, actually. That's really stunning, Daryl. Look at that. Daisy and Zoe, I know why you like this so much.
They have good taste.
They have really good taste. You got it. You know? And those colors are just stupendous. Since we know that this is the Horsehead and Barnard 33 as well as the flame, which I didn't put up here, I'll take that out for now, just so we can look at the beautiful view. This is Alnitak. It's an O star, its own star, like an O7 type star, one of the hotter and bluer stars in the entire universe. And this one is, again, comprises one of the 1 to 2% of the stars in the universe, and it's going to go supernova eventually. It's currently assisting in illuminating some of this nebula, causing it to glow, but there's other stars inside this nebula which are also ionizing some of the hydrogen in there as well. And again, reflection nebulae. This is the glow that's being caused by Sigma over here on the right that we talked about. And this is just, the Horsehead looks really pretty tonight. Let me see if I can do a little push. You can see that star now right there. You can see the star inside the horse's mane right there. You can see the star inside the horse's nose right there. Another one out there. One right in here. Fantastical stuff.
Yeah. Izabela asked, what is on the right side out of frame? Is there something interesting there?
Oh, well, I mean, we do have a more of this nebulae that's over here to the right, and you can see there's more out there, and it's a bunch of softly illuminated, softly glowing, I should say, stuff out here. Let's see if we can process that and bring that in. Let's see here. Pull this down a little bit. Pull this up a little bit.
The whole molecular cloud, it's just vast. It covers like most or all of Orion.
Oh yeah.
We've shown deep exposures of the whole constellation before.
Yeah.
Some parts are lighter, brighter, some are dimmer and darker, and about got it all there.
I love the subtlety. Look at this. You know, the subtlety in the flame is really quite nice. In fact, if we will this get rid of us? Yeah. So this will allow you to see this right here. That beautiful location, which has some emission nebulae and reflection nebulae in it. More reflection nebulae here. Just beautiful. And this subtle coloration is from the molecular cloud. Go ahead.
When we look at Caspar and the Boogeyman, I mean, they're just to the upper left of the flame, aren't they?
Yeah, they're just out of shot up there.
Yeah.
So we did 18 here. We're going to pause this now and save this. And this is primarily the Horsehead, but the flame is in it. And usually it's in for all of them. So we'll save this. All right, so that's our astronomical format. And now we'll save it exactly as seen, because that is just spectacular. And one more zoom just for fun.
It's nice to catch the flame like that. It's very
Look at that.
all the variation, gradation.
Yeah.
A little more
3D.
subtle. That's really beautiful.
It's pretty 3D, yeah.
I like that. Yeah. A lot of times you see the flame, it's washed out.
Yeah, but look at this.
Overexposed. Yep.
So we're catching a lot more than we normally do, which I'm really happy for. Okay. All right.
If you like that deep exposure of the whole constellation, I've showed it to you before.
Oh, yeah, yeah. I actually want to make one of our own. You know? There is no real-time application to remove the lens flare. That's a visual artifact. Has to be removed. I don't have an occulting disc, which would kind of accomplish the same thing, but it would move the star too. But this is beautiful. Okay, we saved this already, so we're gonna leave this alone here, and now head to another object that's gonna show up probably just as beautiful. And all right, so let's go back to our planetarium shot here. Yeah, we're gonna come up here, and this is where we're gonna go next. I think it's like, well, it's actually really close here. Let me just get here. We're gonna go to LDN 1622 first, because it's right there. We don't have our Lens Bright Nebula stuff done, or that we're doing right now, so we're gonna actually bring in different catalogs. So deep sky objects, Barnard's, Sharpless, Lens Bright Nebula, and then of course Lens Dark Nebula. Okay, and that's good for now.
Yeah, if you can show there where the flame is, where we just were, and where we're pointing now, like I said, you see there's the flame and Alnitak right there, and then just above to the upper left there.
That's the Boogeyman. Yeah, and then right here is Caspar the Friendly Ghost, so that's like right above it, kind of along the same line. This faint red thing you see, this is Barnard's Loop. Now we're going to image this, okay, now, and you'll see Barnard's Loop to the right of it. Then we'll image Caspar the Friendly Ghost, and you'll see Barnard's Loop to the left. So you can imagine we could do a mosaic of this whole area of space, and you can see it'd be 1, 2, 3, 4 big shots. I'd like to do that, but I want to get back to the Comet at some point. So we're going to do this and the Caspar shot, and then we'll go back. First, let me just bring back our telescope computer there. And now let's go over here and look at Lens Dark Nebula 1622, otherwise known as the Boogeyman. Here we go. All right. The Boogeyman. You can kind of see it already. Let's bring up our sensitivity some. Okay, we can see some stuff there. We're at 50%. We can actually drop this down a little bit. And this is the Boogeyman right here. So what we'll do is we will let us guide. We're guiding now. So we're going to do a 50-second shot of this object. There we go. We're going to dive into the darkness of the universe, guys. And we will see the location from which life itself is generated, which is all this dark dust. And this was our last shot. That's up on the server for you to download just like you see it. Hello, Patricia Slammer. How are you? Thank you for joining us tonight. Hope you'll subscribe and enjoy us with us. All right, this next image will be the first image of our next object, the Boogeyman Nebula, or LDN 1622. It's a dark nebula region, which is just amazing for its, well, not yet it isn't, but now it will be when you see this. There it is. All right, and as we keep going, it will look really pretty. I'm going to change this name now. Okay. All right. This is Boogeyman Nebula. That's a colloquial name. It's actually LDN 1622, which stands for Lynn's Dark Nebula 1622. Okay. Amazing. You're going to watch some magic happening here in just a few seconds as this starts to come in. There's 2 images in the stack right now, and it's going to get progressively better and better and better. I promise. We've seen it all before. All right. There's a lot of data being captured here. See how much stuff is in here? We overprocess just to show that, and then we go back. And then we use these processing tools down here. Okay. All right. There's our main curve right there. So we can now ride up and down this curve here, and you can darken the background and bring out more of the detail that's living in the shadows. Look at that. You'll notice down here there's a star and this whitish nebula. It's actually a reflection nebula down here. And we'll color correct this too to get our curves lined up. And that shows you a little better what we're looking at. There we go. And now we can pull this in a little bit. There it is. Look at that. See, this has got these little detached pieces. It looks kind of rough right now, and that's because of the fact that we have to pull in more frames and stack more to get rid of all that noise. And as we do, this is going to start looking like a very, very cohesive image. Absolutely beautiful. I'm reading some comments here. Patricia Slama, thank you so much. That's very kind of you. And I look forward to having you in our streams, you know. So make sure you subscribe and give a thumbs up. Help us make some tracks on YouTube. Let's very pretty. Okay, let's do a little more processing here. Let's see where it wants to go.
Do you think the bright red star is just a foreground object?
Well, if it's a red star, it means it's a lower temperature star, probably not responsible for doing any of the hydrogen emission, because it's not probably not pumping out enough ultraviolet to do that. So here's what we could do. Now let's go here. Let's center up on this object, and this is the red star we're talking about right here. This red box, by the way, represents our field of view. Okay, so that's our whole field, and this is 56 Orionis. This is the star. It's actually a let's see if it gives. Yeah, it's a K2, 2b. So it's actually a supergiant star. All right. So it's a big supergiant, meaning it's distended in size, and therefore not very hot. So it's not pumping out an awful lot of ultraviolet energy. So we can look up 56 Orionis, right, and find out just how far away it is and how far away the Boogeyman is. So you might want to do that there.
Boogeyman is about the same distance as the rest of Orion. It's about 1,500 light years away.
All right. Look up 56 Orionis then. See how far that is. Maybe we'll do a correlation here. It could be foreground, like you said.
Six Orionis is approximately 1,130 light years from the sun, based on parallax.
Okay, so it's almost the same distance, but again, it's a 2b, a Roman numeral 2, little letter b, so it's actually a supergiant star. So it's gone through its evolution. It's probably depending on its spectrum, we'd be able to know whether it's been a red giant before, or this is the first time it's been a red giant.
K2-2b, is that what you said?
Yeah, I think it was a 2b, not a 3.
Suspected variable star.
Yeah.
It's a red giant. Having exhausted the supply of hydrogen at its core, the star has expanded to 92 times the radius of the sun.
So it might be moving up what's called the red giant branch, which is the first step in its evolution. Does it say what the mass of the star is relative to the sun?
.4.
Okay, so that means
6.4 times the mass of the sun. It's about it's a little over 2,500 times as bright as the sun.
Yeah, for this luminosity. So what that means is that this star is becoming red giant for the first time, and if it's 6 times as bright, or sorry, if it's 6 times the mass, then it falls in that 4 to 8 solar mass range. So this star is, if it's in a red giant phase, it probably hasn't started fusing helium into carbon in its core yet. So it's making its way toward doing that, but it might not have what they call the helium flash. It's probably going to be a subtle change. It'll start fusing helium. It'll start turning a little more blue as it evolves, and then it's going to end up exhausting the helium, and then it's going to start this unstable burning, which is actually going to contract the core and cause it to expand more and go into a red giant phase again. So that's going to be the what's called the asymptotic giant branch. So based on everything you're telling me, I think this is the first time it's been a red giant, because stars will be a red giant twice in their lives in general. The first time is when they exhaust hydrogen, and then the second time is when they exhaust helium, which I think is, it's cool to kind of think all that through. But this is indeed the Boogeyman Nebula. Look and see, the details are coming in better now.
Yeah, the 56 Orion is there.
Yeah.
That is something of a foreground object, I guess.
A little closer, right?
If
A couple hundred light
if the
years.
numbers match, yeah, a couple hundred light years. If it's 1,100 light years, and they said the Boogeyman's about 1,500, like much the rest of the Orion cloud, of which it is a part. So 56 would be in front of it somewhat.
Yeah. That's beautiful.
Good night, Jose.
Oh, it's Jose Santos. Okay, Jose, thank you so much for coming to us from Lisbon. You have a good day, and we will talk to you later. Thank you very much for joining us. Make sure you subscribe. Leonardo Vital, how are you? Hello
Marc,
to you as well.
Izabela wants you to bring the clock back on the screen.
Oh, I think I probably should. I was doing that to show this, but you're right. She's absolutely right.
She says it helps her when she does her table of contents.
Okay. Thank you, Izabela, for the reminder. On my left screen, I have the observatory broadcast, and on the right screen, I have the broadcast software sending out the stream. So I have two eyes, so I can see two directions, All right. Okay, we have 15 frames.
Oh, that's really building up now.
It is. We're going to let that go a little bit longer. Can you handle... you can handle this vast crowd while I go take care of something real fast?
Sure.
All right. And we have 50 people who are watching us right now, and I want to thank you all for coming. And I'll be right back. I leave you in the capable hands of Daryl Mason. I'll be back.
So you got to put up with me now. We're going to go back to the Comet soon, folks. I know that's the star of the show. We just always wind up exploring what's around it. And if I remember correctly, I'd have to look up the comet's path through the sky. It's going to keep moving it's by Mars and Taurus now. And I believe it's going to drop down through or right next to Orion in the coming days and weeks. I'll have to look that up. I'm not sure if it'll oh, shame on you, Izabela. Go ahead, give me a question. We may see the comet. I don't know if it's going to go next to Orion or through Orion. I'll have to see. You got a question, now's your chance. I'll try to keep it short and sweet. Haha. You see the spider web dancing around in the picture over on the left margin of the telescope in the observatory. That's a spider web getting blown around by the wind. I'm almost surprised the image is staying as good as it is. The moons have their own moon satellites. Izabela, that's a good question. I'd have to think about that. Moonlets? What astronomers have I met? Do you mean famous astronomers? None that I recall.
You never met Clyde Tombaugh?
No. You did, of course.
Well, I was just wondering.
No, I said once, when I was in Las Cruces, New Mexico, to see the annular eclipse down by El Paso, Texas, back in 1994. Yeah. I stayed in Las Cruces, New Mexico, and I knew he lived there then. And I thought about, gee, wouldn't it be neat to meet Clyde Tombaugh, but I didn't have the nerve to bother the guy. And yeah. As you said, he was such a friendly, down-to-earth guy, he probably would have been nice.
I know he would have. I mean, the guy, yeah. He was very humble, and he loved talking about his craft. You know, he had no arrogance whatsoever. You know, and I learned a lot from that. You know,
well, he was a farm kid from Kansas.
Yeah,
about as down to earth as they get.
Yeah, I kind of saw that. I admired his personality, and I guess in a sense I try to emulate that. Right. We're just passionate about what we do.
Yeah.
Look at the Boogeyman. This is gorgeous, man.
Mm-hmm.
We're seeing a lot of data in this image that isn't even fully processed yet. You can see the subtleties in the color here.
Can you zoom on a bright thing to the lower right of the Boogeyman?
Right there, yeah.
Yeah.
I just want to make a note that to this side of the Boogeyman, there's a subtle, wispy structure that is starting to be visible here, but it's only visible in deep processing, and it looks like a wake, but it might be the result of stellar winds pushing some of the dust further away. Let's zoom in on this part here that Daryl's asking about.
I know we've seen this before, but
that's okay.
It has an almost kind of a yin yang shape to it.
It does. Let me back out a little.
See the dark blob there to the right of it.
Yeah.
And a little dark tail curling under the bright part. Pretty cool.
Yeah. So this is show you a little more about what that is. See, to show this, we have to overexpose that. To show that, we have to underexpose that. You know? That's really cool.
I was just curious. Thank you for doing that.
Yeah, sure. No worries, man. Not a problem. Alright, let's now we'll zoom out of this. All right, we've done 22 of these. I think that's good. We'll be able to process this. Look at the colors. This is stunning. Again, this right here, slide that out there one more time. This is the Boogeyman Nebula. It's a dark nebula made of dust that is tiny little spindles, mostly silicates and carbon compounds and carbon molecules. So we'll pause this right here and save it. We've already got the name. So there it is, and there it is. Okay. Now we'll do one more in this region. For one thing, let me just do this. Let me just zoom out just for a minute because I want to show you something else. Okay, down at this lower right corner, right, that you see right here. Actually, it's kind of better to show it like out here. This right here is the left edge of Barnard's loop, which is a big, thick loop of hydrogen gas that is the remnant of an ancient supernova in this region. And on the left side of it is the Boogeyman Nebula. On the right side is the next thing, which is down right around here, actually. So let's go check that out. So let's get out of this and go back to looking at our night vision shot and zoom in enough. As you can see, look, you'd never know this was there. You'd never know this was there. Okay, so we're going to come out now, go here, and now we're going to come down to this guy right here. Alright, this is the Caspar the Friendly Ghost Nebula. This is stunning, and as you'll see.
We're on the other side of Barnard's loop now.
That's what I said. Exactly where we're going. So there is the other side of Barnard's loop right there, that subtle glow. That's the lower right side of Barnard's loop, and you go this way up there, and it'll take you to the Boogeyman Nebula, which is now out of our view. So what we're going to do now is I'm going to bring us up. Alright, and just bring us over a little bit to the east. Right. I see Leonardo Vital says this green comet Lanterna Verde inclusive está funcionando pelas. Not getting quite all of it. Is that Spanish or is that Portuguese? I don't know. Eric Gage, hi. Unrelated to the comet, but have you heard about the possibility that the supermassive black holes formed from stars early in the universe that were bigger than hypergiants? I think that is a theory that is out there, and any theory is as good as any other when it comes to that, because supermassive black holes had to start somewhere, didn't they, as you say? So I'm not sure. And if anybody knows what Leonardo Vital is trying to say, can you please translate that for me? I don't get all of it. I think it's not Spanish as much as it might be Portuguese. I don't know. Or maybe it's another language. Okay, let's just focus here. We're now guiding properly. And we're going to go up here and we're going to do a 55-second shot of this. And away we go. Okay. Now, I think you guys will be happy to see the result of this. We talk about dust. You're going to see dust. Eric H. says, yeah, I just thought the theory was interesting. It is. It is very interesting. Sorry, Daryl. Didn't mean it. Okay, the magnitude of the comet is now 6.3. Alright. Ray. So, just so you know. At least that's what they say it is. Okay, that's good. That'll work. So now, let's stack that. We'll clear this stack, because it's up on the server, which you can get to from going to SkyTourLive.org, SkyTourLive.org, and scroll down, and you'll see instructions and a link to get to our free server, where you can get all the pictures. They aren't hyper processed, but you're going to get the raw shots like you see here, and you can take those and use those if you like. You just can't sell them. But then, if you want the other much more beautiful shots, then you will end up. You want to join one of our upper tiers.
Izabela translated.
I see that.
Portuguese for you.
Thank you, Izabela. Well, it's very interesting. I'm not sure I can agree with all of it at all, but it's I think that's kind of cute. Home of the Green Lantern. Yeah, okay. I mean, the Green Lantern's home planet is cyanogen, so it's poisonous to us. If that was true, that'd be kind of funny. We've only got one image here so far that's been stacked. So we got 7 seconds until the next one comes in. 1 second, and you'll see the noise go away a lot more. Yeah, look at that. Now you suddenly start to see these wisps much more clearly, and it's just going to get better. Look at the beautiful color of Barnard's loop up there in the upper left corner.
Yeah, very distinct.
Mm.
And sharply, what would you call that? The band running the.
Yeah. You might want to talk a little louder, Daryl, because you are getting soft as it's getting later.
Okay, sorry, I'm getting tired.
I can tell. That's okay. I just letting you know. I don't want you to mistake it for you not having your volume up high enough, you know?
No worries.
Good. Thank you, Izabela, for putting that up there.
Well, you're doing deep exposures, aren't you?
Yeah, we're doing 55 second exposures here. I wanted to capture in the Caspar this beautiful region here. I wanted to capture this beautiful cascade of dark material. And you can see it starting to come in already. And if we bring this in, okay, it's going to show it better, but it makes it too bright, right? So what we do is we have to darken up. We have to pull this guy in to darken up, go right to the peak, but not really past it, because we don't want to ruin what we have, okay? But that's kind of what I'm saying right there. That's the highest we would ever go, and as you can see, it gets noisier. So we'd pull this down a little bit, pull this down a little bit. But you can see how there's so much in here, but we'll let it set up where it wants to go, all right? And then we will play with that from there. Okay, so right there is good for now. And again, using this one over here, we can see what else is in there. There's more detail in there. But we'll pull that out, because that adds a little too much noise. I want to show you also inside here. This is more reflection nebula up here, right? So again, the star's light in here is being scattered by the dust that's here, and that's what creates the blue color, because blue light is easily scattered by the tiny dust particles that are here. And as we move out here, you can see that there's actually 2 stars in here, and there's 1 star here that is responsible for doing this scattering. Okay. Just beautiful. You can see Barnard's loop here. It's really beautiful showpiece. And this material over here, there's not much over here, but this part here is really just full of beautiful material. Again, the beautiful mixture of dust and hydrogen gas that is responsible for the creation of stars and more planets. So this dark material here, this is one of my hot buttons, because when I got my degree in astronomy, my focus became exoplanets afterwards. And exoplanets come from something. Well, where they come from is these dark, cold regions in space. This is where planets are formed, as well as stars. And when stars kind of wink into existence, then they illuminate and cause to glow the hydrogen gas around them, and we call those stellar nurseries. But there's always dark dust in these stellar nurseries, because the stars could exist from the hydrogen gas, but the planetary systems around them, if they're there, come from all this dark dust that's also there. That's called the nebular hypothesis, and it's exactly how we think our solar system formed and how other planetary systems formed. We've since found, as Daryl will be able to attest to, because he's also the co-host on SkyTour Radio with us on Sunday nights from 6 to 8 p.m. Eastern Time on KGRA. SkyTour Radio, we've talked about the fact that this dark dust is throughout the universe. We've actually seen it, talked about it, and actually dove right in deeply to talk about how planetary systems form, the nebular hypothesis, and how the James Webb Space Telescope, we just did this actually, was a couple shows ago, Daryl, I think. We actually showed one of the stars in Microscopium, which is a constellation of you guessed it, microscope, has a dust disk. And it turns out that the dust disk is scattering the shorter wavelengths of light more efficiently than the longer ones, which is what we see, which is consistent with, in other words, the short wavelengths of light are the blue light. And so the bluish light gets scattered very easily, and the reddish light does not. So, really interesting. Oh, I see. Thanks for answering Donald Kunzer's question there.
Yeah.
Now you can see that more exposures have come in. You can see now there's more subtle variations in this material and the brightness. And now we might be able to support pulling this in a little bit to show just how much more subtle this region is. Look at that, Daryl. There's a lot of really interesting material in there.
Donald, you asked if the dark cloud is part of the loop, part of Barnard's loop. I said no. That might be debatable. I mean, if you saw all of Orion and where the Barnard's loop is, it is just the one supernova remnant out of many in the constellation Orion. And all those supernovas together have produced the dark clouds you see. I guess it would be fair to say, that when the supernovas return their elements back to the molecular cloud, the end result there is the dark stuff you see.
Yeah, the dark material can form in the outer atmospheres of supergiants, red supergiants, because the stars are so distended, so large in diameter, that the outer reaches of the star are cool enough. They're still hot. You'd never survive flying through there, trust me. They're about 2,500 Kelvin or 3,000 Kelvin out there. But they're cool enough so that molecules can form. and those molecules will be molecules of carbon atoms together, or molecules of silicon that the star might have been made of, that's been puffing off over time. And over time, this dust will just permeate the universe, especially in the spiral arms of galaxies, which is where we are. We're looking in the Orion spur of our galaxy's spiral arms here. Michael Klages is here. That's Rocket City Astro right there. Hi there, Michael. How are you? No, you didn't miss the comet. We're going back to it shortly. We just took the opportunity without a moon to start looking at some gorgeous objects like the Caspar the Friendly Ghost Nebula, Messier 78 here. And it's just, the subtlety is overwhelming here. It's incredible.
If I remember right, the moon will be up just before midnight tonight from Arizona.
Yeah, so we're at 10:30 right now out there. We'll start getting the glow of the moon on the horizon in the next hour or so. And that's okay. Because we're going to check out just another object or two anyway tonight. Oh, this is just beautiful. Again, you have to understand that when we take images of the same objects over and over and over again, the purpose of this is several fold. Number one, they're beautiful objects. Number two, you as individual viewers can go take these images and compare them to images taken of the same object in months or even a year past or more, and see if there's any subtle changes. Are there any stars that were there that were not there when we took the picture before? And you don't have astronomers looking at every object in the sky all the time. You just don't. Okay, so let's say we zoom in here, right? Let's just do this. Okay, let's suppose we zoom in, and we're looking for differences in what the sky is showing us now. Okay, well, what if we look at this object right here? Okay, there's 3 little stars right there. Well, what if you look at a view from a year ago, and there's only 2 stars there? You will be credited with the discovery of a new star that has winked on. The International Astronomical Union will recognize that you found it, and will say, found by an amateur astronomer, found by a viewer of SkyTour LiveStream, and you'd get credit for that. So we're doing a lot of repeats so that you can actually also possibly find something that's never been found before. And we would be proud to have supported that effort. So wherever you look in the sky, you might find all kinds of things. Right? All right, so that's the philosophy behind why I will image the same object over and over. Thanks, Eric. Good to see you. Eric Gage is taking a train out of town for the night. Look at this. There's just so much detail in here that shows up once we just... Remember this stuff wasn't looking so subtle? It was looking kind of muddy.
Yeah.
Look how clear it is now.
Can you zoom in on that dark part, the lower right hand part?
This here?
Yes.
Yeah. All right, let me bring this back.
See what the little red thing and the thing next to it.
You're talking about this right here.
Yeah.
Looks like a little string of stars, and this looks like a tiny emission nebula associated possibly with this star. Let's try softening this a little bit by doing this.
See some dark tendrils.
Yeah.
Running down to the lower left. They
Here?
look real. Yes.
Yeah. I believe those are real. Here. In fact, if we zoom out, you can see how that likely is real, because it looks like it connects to here. There's all kinds of little tendrils there. You know, so let's sharpen that up again. Yeah, look at that. That's definitely a very, very detailed look at this area. Holy cow.
What's Caspar's designation?
Measure 78.
Well, I thought.
Good night, Judy M. Thank you for coming. We have 55 wonderful people watching us right now. Welcome to SkyTour livestream. Just a little refresher for those that don't know. This is our telescope control section over here. This is our telescope computer, which is currently off. This is the video, or the image of the telescope live out in the building 2,500 miles away. This dumb looking guy, that's me. This is our current stacking system. We're stacking images, making an image sandwich, and then getting the data to be clearer and clearer. This is our gorgeous main view, which we can go to full screen sometimes. This here is our camera control section. This is our focusing segment, and again, the main view. If anything of interest happens, here's the time to note at that moment, and you stick it in the chat. All right, so that gives you an idea. Lastly, the most important numbers to look at when we're doing this is the exposure. That's how long we're exposing this system, and then this is the gain. That is how sensitive we're making the sensor. The larger that number, the more grainy the image will look, the more noise we'll get. So we tend to stake around 300, and the long exposures with the high gain tend to get rid of the noise. As you can see, these look really, really pretty, and it will get better and better and better as time goes on. And that right there is a primer in what we do. You can see the color of the dust here is actually a brown, and it will end up mixing with this hydrogen over here, which is being caused to glow by other stars and ancient energy from the supernova from whence it came. Just beautiful. Okay, so we're going to go to 20 exposures on this, and then we'll stop and move on. Maybe we'll go back to the Comet after this. Okay, so now we're going to change this name to Measure 78, which is M78. That's to be the Caspar, the friendly ghost nebula. And that is the EN emission nebula. I'm sorry, RN reflection nebula, and space DN for dark nebula. But don't worry, you'll get that over time. All right, so now we'll save it. There we go. And save it exactly as seen. There you are. So once again, if we click on that, okay, this is the image that you're about to see. This is what's going up there right now. We can pull this name out for now. So this is what is going up on the server right now, complete with all this beautiful detail in here. All right, so we'll take that away, and we'll now clear this because we've already saved it all, and move to the next object, which I think we said would be the Comet. So we're going to try going to the Comet again now, and we'll see. Last time we looked at the Comet, there were two stars. I lined them up, and you could see how the Comet's nucleus was just sort of lined up with them, and then over time, the Comet nucleus changed position. Well, we're going to see the same thing, except now it's going to be even more drastic. So here we go. We're going to the last known coordinates for the Comet. All right. And there we go. We're on our way now. and it's really pretty far over in the west right now. There it is. Last time we came here, we were looking here, but now the comet's down there. So let's get ourselves going here. Let's bring the comet down into the view. I would say we've had quite a lot of the green comet in the last couple of weeks here. Wouldn't you say?
Excuse me. Oh, yeah.
Okay.
Sorry, I was playing with the comet's orbit over at Sky Live.
That's all right.
It looks like it's close to Mars in our sky.
Yeah.
It's actually out between Earth and Mars.
It's up there out of the view. Unfortunately. I'm trying to see. All right. Okay, well, let's just take a 35-second shot now that we're guiding, and let's see what we got. Let's see how it looks. So our live stack will show that we are waiting now, and we have 25 seconds. DS, can we get the green comet and Mars on the screen at the same time? We had intended to stream last night, D, when we could have. The comet's moving fast. Mars is actually a very overbearing bright orange blob that makes multiple reflections and reflection rings on our screen, so it's very, very difficult to actually get it to show properly, you know. And if we want to show any detail whatsoever with Mars, the comet would be a very, very low brightness, like way down, you know, well below this. So let's see if we can move this over and get a little better. You can see the tail here, the plasma tail. It's very faint, but you see the blue there. Here's the blue plasma tail. It's just there. See that right there? Just barely there. But there's the dust tail of the comet right there. That dust tail is basically behind us into the page, so to speak, and behind the comet as it's moving through space.
I think the tail looks even skinnier.
This
The
one?
dust tail.
Oh, the dust tail?
You know, the fan seems like it's closing up on it.
Yeah, and that could
From
be
our point of view, it looks narrower.
that could be a function of this processing too. You have to be careful. I got to be careful, I mean, so that I could make sure we show it in the same way that we have been. Because what you're seeing could be a real effect or not. It just could be dependent on how I'm showing it. You know what I mean? So I don't want to be misleading either. But it does look narrower, doesn't it?
Uh-huh.
Okay. And that's it. That's our green comet. Well, McCain found Measure 42. That was McCain's Nebula, actually. That was Measure 43. I'm responding to Daryl's comment. McCain found quite a few of the Measure objects in the chat, he says. And that's True, and most likely, they most likely were many coincident discoveries that people made.
Oh yeah. Well, I was responding to Ray's comment.
Yeah, Ray had said that Caspar the Friendly Ghost was probably was not discovered by Messier, but discovered by Pierre McCain in 1780.
Messier had, I forget how many. There were several people contributed to the list.
Yeah. All right.
Thank you, Izabela.
Wow, thanks for putting that up. Very good.
That's interesting. I just opened that when she posted it, and the
Yeah.
little red area we looked at in the dark nebulosity to the
Lower right.
lower right, it looked almost like the face on a jack-o'-lantern.
Okay.
Got slanted eyes and her nose, and then a crooked mouth over to one side like he's leering.
Huh.
That's pretty neat.
That's cool. Okay, we're gonna clear this to get a second singular shot, just for location purposes.
Izabela, how they used to find new objects then.
They would just scan the skies.
Yeah. Messier's thing was comets, and that's what he was looking for, and he started his list, of course, to make a list of things that were not comets. Somebody had to be first, and one guy just missed it, and the next guy saw it, any particular thing, and was there rhyme or reason to how they were searching the sky? I'm sure they had parameters to search programs, and they knew what setting circles were on telescopes by then.
Yeah, they were grid searching. They were doing grids.
Yeah.
No.
Way back Ptolemy? I don't think even he was the first. They had, they were studying the sky before they ever had telescopes.
Yeah.
They had degree wheels, all that stuff, that they could try to break down, and locate objects within the sky. And they noted that some objects were moving, of course, but I'm sure there was some rhyme or reason to how they were doing it. Search grids, as Marc said.
Okay. We're going to, this is only 4 shots here, but we don't want to do too many with the Comet because it moves so fast. All right. So this is excellent. And what we're going to do is we're going to do one more object tonight. And So let's go off and do that. This will be up there for you to see. We saved it. Alright, and let's go check it out later. Right now, we're going to do this and move to our final object for tonight, which never fails to impress. And that is the beautiful Seven Sisters, known as the Pleiades.
Centaur Flyer, how often do you live stream? Is there a regular schedule? It's dependent on the weather, the dark of the moon, the bright of the moon, factors. I'm sure Marc could say more.
You're saying it all. That's pretty true. You know, it depends.
Yeah, it depends.
Yeah.
I mean, if it's, believe it or not, it rains in Arizona sometimes, and if it's cloudy down there, we don't stream.
Right. We do get, on average, about 300 clear nights a year for real. I mean, that is true, on average.
That's what they say here.
Yeah, but as you said, that usually means, you know, in the daytime or in the morning is clear.
In the morning. Yeah.
Yeah.
They like to brag 300 days of sunlight a year. And with the summer monsoon here, which Arizona suffers from some also.
Yeah. In June.
What they don't tell you is it's often in the morning here in Colorado.
Yeah. Okay, back down.
D asked, if it moves so fast, how has it been in our view for so long?
That's a very good question. Well, the way to answer that, D, is that it really isn't. It's only here for a few weeks. And that constitutes a fast-moving object. However, we also have asteroids. It depends on how close they get to us, too. There are asteroids that pass between the orbit of the Earth and the Moon. And when they go by, you could visually watch them traveling through the sky in a telescope appropriately equipped. This telescope would be able to see some of those traveling through the sky. So there are plenty of fast-moving objects. And asteroids like that might only be visible for like 2 or 3 days as they make their trek through our inner solar system and zip by the Earth. Sometimes they're not captured until after they pass us. But, you know, we're working on it. Centaur Flyer says it's 28 degrees Fahrenheit and clear in Central Oregon tonight. That's cold. All right, I'm going to do something right now. I'm going to come out here and do an acquisition here to see. 15-second acquisition. We're going to see if we're still clear out there. We may have some clouds moving through. Let's find out, shall we? Here we go. Yeah, I thought so. There they are. See, we're right here. And this is the Pleiades. This is Orion. See the belt? There's Orion's belt right there. Betelgeuse. Okay. Mars, Aldebaran. Comet is right about there. So we're actually running into a few clouds, which is what I thought I saw. This is our all-sky camera, by the way. That's a bird turd along with that. Birds like to sit in our camera dome out there. It's convenient for them. See the clouds?
Yeah.
I was going to end with the Pleiades, but it won't be a very good shot. So that's all right. It sort of aborts our shot for now, but that's okay. We'll be doing more. I promise you that we'll be back in the coming days. And as far as the frequency, as Daryl said, depends on the weather. But if it's clear, we'll be doing it. So hopefully you guys will like to join us and keep sticking around. Make sure to come check us out. We are going to close up the stream and be done for tonight.
Marc, Izabela had a question before we go.
Okay.
She had asked, if other astronomers confirmed astronomical discoveries. And I said, they used to just write letters to each other. And there's a central clearinghouse to this day. Where is that? I forget.
The International Astronomical Union, the IAU.
Well, there's the IAU, but then there was first notices went to some college, some university. Harvard Center or something or other.
Well, there's the Harvard Center for the Harvard Smithsonian Center for Astrophysical Studies. There is a reporting. What's the name of it?
That's what I'm trying to think.
I've called it. I've sent stuff into them.
Yeah.
And I can't think of it offhand. Figures you when you're asking a question like that, especially at 1 in the morning here, you just don't think of it.
Sorry.
No.
Ultimately, yeah, it does go to the IAU.
Yeah.
They make the final call, and they decide who gets to name it, or what the name is going to be for an object, et cetera, et cetera.
And if you're the first one to find the object, you won't have that taken away from you. They might share the name if there was a co-discoverer. Like suppose we found a star that winked on in the Orion Nebula somewhere, or in one of the other objects we did, like Measure 78 or the Boogeyman. Suppose one of you out there, found something out there. You'd get credit for it in the list. And if someone else found it at the same time, it would be, like the Mason Dantonio, star discovery in Measure 78 or something. And it would be named appropriately. And the IAU determines the actual name. But you'd get credit for the discovery.
The place that the clearinghouse people did report to, it was like something or other telegrams, I want to say.
Yeah.
People used to actually wire in their findings.
I don't think they do that anymore with email and
sure,
instantaneous stuff.
And I can't think of the name of the astronomer who, the well-known name, who I think who ran that for many years.
Yeah.
Anyway.
All right.
Thanks for coming, everybody.
Yeah, Izabela asks, what have I discovered? When I was getting my degree, I studied B stars, not O stars, but B stars, the next hottest star, and discovered a number of them that were speeding out of our galaxy at high speed. And that was something unheard of, but suspected. And it comes from these OB associations, which are O and B stars together, that make these associations of stars all moving kind of in one direction. And sometimes those stars are gravitationally interacting, and one member might get whipped out of the cluster and get enough speed to escape from the galaxy. And I found a number of stars doing that. And that data was published and put out there, and so I think that's pretty interesting, for what it was. Okay, guys, it is that time, and I am very happy to say that this was a good stream. You guys are phenomenal. It's great spending time with you, and hearing that music, you know what that means. It means it's time for the stream to come to an end. We start and stop with the same music. All right, guys. Thanks for coming. This has been a wonderful SkyTour live stream. Thanks, all of you. Go to SkyTourLive.com or SkyTourLive.org. Both of those work. And check out the SkyTour live stream on the upper left and SkyTour Patreon in the upper right. And think about maybe subscribing to the Patreon supporting us. We run on your support, you know. In any case, you guys have a good evening, and we will talk to you the very next time we stream. All right? Thanks, folks. Good night.
Good night, everybody.